In our last class, we looked at combining voltage sources in series, current sources in parallel, and resistors in both series and parallel, and we started looking how we can use these concepts to solve some circuits. In today's lecture, we're going to continue this topic mostly with examples basically showing a variety of things that you can and cannot do by combining sources and resistors in series and parallel. In this first example, we have a whole bunch of components all in parallel, and we're asked to find the voltage V across this parallel connection of sources and resistors using source and resistor combinations. So we see first off that we have one node on the top and one node on the bottom, and that every component is in parallel. The idea here is to replace the three current sources by a single equivalent current source. We'll call it I equivalent, and I am arbitrarily orienting it with the arrow pointing up. Doesn't necessarily mean that that is the direction that this current source is going to take, but that is the direction we're using for our reference, and we'll see how that comes out in the problem. And then the two resistors have an equivalent resistance. We will call it R equivalent. And the voltage variable that we're measuring is the voltage across these two nodes, the yellow node and the pink node, which are still there, and that is still V. R equivalent is the easier of the two things to find. It's basically the parallel combination of the 300 ohm and the 150 ohm resistor. So 300 ohms in parallel with 150 ohms. You can find three different ways. One way is the general equation that always works. It is the reciprocal of the sum of the reciprocals. However, because there are only two resistors, there is an easier equation. With two resistors, you could also find the equivalent resistance as the product over the sum. Slightly easier equation. But there's a third way that's even easier. We can recognize the fact that these two resistors in parallel are a ratio of R and R over 2. R in parallel with R over 2 is R over 3, or 300 over 3. Regardless of which of the three equations you use, you get an equivalent resistance of 100 ohms. I equivalent, once again, a little bit trickier because we do need to worry about signs. So I arbitrarily put the current arrow going up. In other words, the current is going from the pink node to the yellow node. To find the equivalent current source value, I look at the three sources and see whether they're in the same direction or the opposite direction as this equivalent source. The 10 milliamp source is going from pink to yellow, so it is the same orientation. So I equivalent will be plus 10. The 20 milliamp is going in the opposite direction, so it's going to be minus 20. And the 5 milliamp, once again, is going in the opposite direction, so it's going to be another minus 5. You add those together, you get negative 15 milliamps. What this minus sign means is that our initial guess of the current going from the pink node to the yellow node pointing up was wrong, and the true current direction is going down. So if we wanted to, we could redraw the circuit with the current arrow going down with the value of 15 milliamps. And once again, the equivalent resistance is 100 ohms. And we're trying to find this voltage V. Now we can use Ohm's law. We know the voltage across a resistor is the current through the resistor times a resistance. We have 15 milliamps going through the resistor. The resistance value is 100 ohms. 15 milliamps times 100 ohms is 1.5 volts. We have to think about which side has the higher voltage. Remember that in a resistor, the current always goes from higher voltage to lower voltage. Since the current is going through the resistor in this direction, this has to be the higher voltage. So we get 1.5 volts across the resistor, with this terminal being a higher voltage than that terminal. Because our voltage variable V has a plus on top and the minus on the bottom, our variable V is actually minus 1.5 volts. In this problem, finding the equivalent resistance was pretty trivial, a little bit tougher than when resistors are in series, but still not that bad. Finding the equivalent current source value is a little bit trickier because we do need to take signs into account. And one thing I want to point out here, when you first look at these current sources in parallel, you might be inclined to think, oh, 20 and 10, they're both going in this clockwise direction. They should add up to 30. That is absolutely wrong. That is not how you add current sources. What you want to think about with current sources is think of the two nodes, in this case the yellow node and the pink node. The 10 milliamp source wants to push current out the yellow node. The 20 milliamp and the 5 milliamp source on the right both want to push current out the pink node. That is why you have the minus sign here and another minus sign there. Final comment, once again, is when we apply Ohm's law, you always need to take into account which direction the current is going, and that dictates which of the two nodes in the resistor has the higher voltage. So this problem, even though it's pretty simple, has a lot of very important details in it. Let's look at another example. In this example, we're not asked to solve for any voltage or current, but we are asked to simplify this circuit as much as possible. So let's first look at the circuit and see what is in parallel and what is in series. If you look at all of these components on the left here, this 1 ohm resistor, this 3 volt source, this 2 ohm resistor, and this 2 volt source, they are all in series. They all share the same current. Likewise, this 3 ohm resistor, this 1 amp source, this 6 ohm resistor, and this 5 amp source are all in parallel. Why are they in parallel? Because they share the same two nodes. There's this node on top that's pink. There's this node on bottom that is blue. This 3 ohm resistor and this 1 ohm resistor here are not in series and they are not in parallel. Although they do share a node up here, they are not the only two components connected to that node, so they are not in series. Furthermore, they're not in parallel because they don't share the same two nodes. The 3 ohm source has this node up here that it shares with the 1 ohm resistor, and then it has another node down here. The 1 ohm resistor has a second node over here on the left, which is not the same. At this point, we can now combine things. The 1 ohm and the 2 ohm resistor here are in series. We can add them together. The 3 volt and the 2 volt source are in series. We can add them together. This 3 ohm and 6 ohm resistor are in parallel. We can combine them together. And finally, this 1 amp and 5 amp source are in parallel, so we can combine them together. So combining the 1 ohm and 2 ohm resistor in series, 1 plus 2 is 3, that's fairly simple. We get that. That 3 ohm resistor is going to be in series with this combination of the 3 volt and 2 volt source. So I will arbitrarily give it an orientation with the plus on top and the minus on the bottom, and see that is the same orientation as the 3 volt source and the opposite orientation of the 2 volt source. So this equivalent voltage source is 1 volt, basically 3 volt minus 2 volt. The fact that I put the resistor on top and the voltage source on the left really doesn't matter. I could have flip-flopped them. I could have put one of them down here on the bottom. It really doesn't matter. As far as the components in parallel now, the 3 ohm and the 6 ohm resistor become an equivalent resistance. Its value, 3 ohm in parallel with 6 ohm, is what? 1 over 1/3 plus 1/6, or 3 times 6 over 3 plus 6, or I could recognize the fact that this is R in parallel with R over 2, which is R over 3, or 2 ohms. And then finally, the 1 amp and the 5 amp current source are in parallel. So I will give an equivalent current source here. I will arbitrarily make the arrow pointing up, and now I want to look. The 5 amp source is in the same orientation. The 1 amp source is the opposite orientation, so this value is going to be 4 amps Once again, that is 5 minus 1. So using the same color coding as before, here are elements that are in series. Here are our elements that are in parallel. And then we have this node up here and this node down here. Sometimes when you start combining elements in series and parallel, it creates other series or parallel combinations. In this example, however, it does not. This 3 ohm and 2 ohm resistor that are left are not in series and not in parallel. That means that we cannot combine them anymore. The 3 ohm resistor and the 1 volt source are in series, but you cannot combine a resistor and a voltage source. The 2 ohm resistor and the 4 amp source are in parallel, but you can't combine a resistor and a current source. So at this point, there's no further simplification possible using just source and resistor combinations. Later, we're going to see that there is further simplification possible using something called source transformation. So at this point, with this example, we saw that yes, you can sometimes simplify a circuit somewhat, but maybe not completely. So the circuit on the bottom here is certainly simpler than the circuit on the top, but it is not reduced as completely as possible, but we cannot go any further using just resistor and source combinations. People are often inclined to combine as many resistors in series and parallel as possible, regardless of whether it's actually helpful or not. There are some cases where you really do not want to do that. As I mentioned before, if you're trying to find information out about a particular resistor, for example, you may not want to combine it with other resistors because you lose that individual resistor's information. Another time you don't want to do that is when you have dependent sources. So if you look at this example here, we have two resistors in series, and you may be inclined to combine them into a single 30 ohm resistor. There's a problem, however. If you look on the right here, we have a voltage-controlled current source that is dependent upon the voltage specifically across this 10 ohm resistor. If you combine that 10 ohm resistor in series with the 20 ohm resistor, you no longer have this variable Vx, and that's going to make it harder to analyze this circuit. Likewise, over here we have these two resistors in parallel, 100 ohm in parallel with 50 ohm. Your first inclination might be to combine them in parallel, 100 in parallel with 50, that's R in parallel with R over 2, that's R over 3, that'd be 33.33 ohms. The problem here is that over here we have a current-controlled voltage source that depends upon this current through the 100 ohm resistor. Once you combine the 100 ohm resistor in parallel with the 50 ohm resistor, you no longer have this variable IY, and so it's actually going to make your analysis tougher. So, rule of thumb, if you have dependent sources, you want to refrain from combining elements that are in series or parallel if by doing those you lose the controlling variable, in this case the Vx or the IY. However, if you really do want to do these combinations, you can still do those, but you have to be very careful and introduce new variables for the dependent sources. So let's see what we're talking about here. So we still have our 10 volt source. The 10 ohm and 20 ohm resistor combined in series give us 30 ohm. The 50 ohm and 100 ohm resistor combined in parallel give us 100 over 3 or 33.33 ohms. We still have our voltage-controlled current source. I'm not going to give it a value yet. You'll see why in a minute. We still have our current-controlled voltage source, and then this 4 ohm resistor. But this is where things get tricky. We no longer have Vx. Vx is the voltage across the 10 ohm resistor. The 10 ohm resistor no longer exists. Instead, we have this voltage, we'll call it Vz. It's a voltage across this two resistor combination. Likewise, we no longer have this current Iy. Instead, we have the current through this two resistor combination. Let's call that IZ. When we find expressions for this voltage-controlled current source and current-controlled voltage source, we need to use VZ and IZ rather than Vx and Iy. But what we need to see is how VZ relates to Vx and how IZ relates to Iy. We will see in a later lecture that the relationship between VZ and Vx is that VZ is equal to 3 times Vx. This is based on something called voltage division, which is a later lecture. Likewise, we'll see that this current IZ is related to Iy using this expression. IZ is 3 times Iy, and this is due to a property called current division. Once again, we will look at that in a later lecture. But now that we know that IZ is 3Iy and we know that VZ is 3Vx, this dependent source is Vx over 20, so its value should be VZ over 60 because VZ is 3Vx. So basically, replace Vx by VZ over 3, and that gives us that. Likewise, here, Iy is what? Iz over 3. So if this is 5Iy, it is 5/3 times Iz. So what we have shown here is that if you do want to combine resistors in series and parallel, even when you have dependent sources, you can do so, but you do have additional work. You have to do this work here, you have to do that work there, and then you have to come up with those. And you may find that it's really not worth the extra effort. Let's look at another example. In this example, we see a source connected to a whole bunch of resistors, some in series, some in parallel, some combined other ways. And we're asked to find the equivalent resistance seen by the source and use it to find the power delivered by the source. Think about the source as your blue blob. As far as it's concerned, it doesn't know that it's connected to a 10 ohm, an 8 ohm, a 6 ohm, and a 3 ohm resistor. All that it sees is that it is connected to some equivalent resistance, R equivalent. What we can do is use resistor combinations to determine what this R equivalent is. The first thing we see is that the 6 ohm and this 3 ohm resistor are in parallel. They don't necessarily look like they're in parallel because they're not straight lines, but if you think about the nodes, they're both connected to this pink node on the top and this green node on the bottom, so the 6 ohm and the 3 ohm resistors are definitely in parallel. Notice the 8 ohm resistor is not in parallel with them. The 10 ohm resistor is not in parallel with them because they do not share the same pink and green nodes. So the first thing we would do in finding R equivalent, let's color code every single node. So we have our blue node, we have our green node, we have our pink node. So R equivalent is between the blue node and the green node. So R equivalent is what? Well, we have this 10 ohm resistor here. We have this 8 ohm resistor here. Now, between the pink and green nodes, we now have this equivalent resistance of 6 in parallel with 3. So 6 ohms in parallel with 3 ohms, which is 2 ohms. Once we do this parallel combination of the 6 and 3 ohm resistor, notice that that is now in series with the 8 ohm resistor. Up in this circuit here, it was not, but in this circuit, the 8 ohm is in series with this combination of the 6 and the 3 ohm resistor. So we can now go another step The 8 plus 2 is 10. Let me keep my same color coding. I think that's useful. We still have this 10 ohm resistor here. And now the 8, which is in series with this 2 ohm resistor we created in the previous step, now gives us a 10 ohm resistor. We can now go one step further because now this 10 ohm resistor that we just created is in parallel with this original 10 ohm resistor. So we now get 10 in parallel with 10. R in parallel with R is R over 2. So this becomes 10 in parallel with 10, or 5 ohm resistors. So we have this simplified circuit now. As far as this 10 volt source is concerned, it just sees that it's connected up to 5 ohms. It does not know that it had all of these resistors it was actually connected up to. It just sees it as a single 5 ohm resistor. So at this point, we can now answer the question. We determined the equivalent resistance seen by the source. It was 5 ohms. Now we could use it to find the power delivered by the source. Well, the power delivered by the source has to be equal to the power absorbed by the resistors. Whether it's the equivalent resistance or the individual resistors, it doesn't matter. So this resistor here has a voltage across it of 10 volts, so its power absorbed would be the voltage squared divided by its resistance. 100 divided by 5 is 20 watts. If this resistor absorbs 20 watts, this voltage source must deliver 20 watts of power. Another way you could see this, by the way, is you could do Ohm's law. 10 volts divided by 5 ohms is 2 amps. So there's 2 amps flowing through this circuit. This source has 10 volts across it. It is 2 amps leaving the plus terminal. So that means it has negative 2 amps entering the plus terminal. And so the power absorbed by the source is 10 volts times the current into the plus terminal, which is negative 2 amps or minus 20 watts, which is what we saw there. It delivers or supplies 20 watts, which is absorbed by either the 5 ohm equivalent resistance or collectively between these 4 resistors. Let's look at another example. Suppose we have 3 resistors connected in a triangle and you want to determine the equivalent resistance. The important thing here is the equivalent resistance depends on the terminals that you are looking into. So let's say that one person takes this triangle combination of resistors and measures the resistance by connecting it up to an ohm meter between terminals A and B. So person A connects up between A and B. So they take this resistor combination and they're measuring R equivalent at this point. 6 ohms, 4 ohms, 2 ohms. For this person, resistors 2 ohm and 4 ohm are in series. They can be combined. 2 plus 4 is 6. That 6 ohm resistor is now in parallel with the original 6 ohm resistor. So R equivalent, in this case, is 2 plus 4 in parallel with 6, or 3 ohms. Suppose someone else measures this resistance between terminals B and C. So they have the same 3 resistors, but they're measuring now R equivalent here. For this person, it is the 2 ohm and the 6 ohm resistor that are in series first, and then that series combination is in parallel with the 4 ohm. So the 2 is in series with the 6. Notice, once again, even though the 6 and 4 are connected at that terminal and the 2 and 4 are connected there, because they are not the only 2 things connected, because we're connecting to the ohm meter, we cannot say that the 6 and 4 are in series, and we cannot say that the 4 and the 2 are in series. Only the 2 and 6. So the 2 and 6 are in series. That equivalent resistance is then in parallel with the 4 ohm resistor. So now our equivalent is going to be 2 plus 6 in parallel with 4. 8 in parallel with 4, R in parallel with R over 2 is R over 3. Let's say a third person takes the same combination of resistors, but they're going to measure the equivalent resistance between terminals A and C. So you still have the same 3 resistors, but now we're measuring our equivalent here. We still have the 6 ohm, the 4 ohm, and the 2 ohm resistor, but now it is these two, the 6 and the 4, that are in series first. And then that combination is then in parallel with the 2 ohm resistor. So our equivalent in this case is what? It's 6 plus 4 in parallel with 2. That's 10 in parallel with 2. Once again, R in parallel with R over 5 is R over 6. So it's 10 over 6, or 5/3 of an ohm. So this example illustrates a very important point. To determine the equivalent resistance of a resistor combination, you have to take into account where that resistor combination is connecting up to the rest of the circuit. Is it connecting up between points A and B? Is it connecting up between points A and C? Or is it connecting up between points B and C?
I have a little demo here illustrating the same concept that we had in the last example. So here I have 3 resistors connected together in a triangle. Values are different from what was in the example. Here we have a 6.8 kilo ohm resistor, a 3.9 kilo ohm resistor, and a 2 kilo ohm resistor. So not the 2, 4, and 6 ohm resistors in the example, but it's the same idea here. And I have a digital multimeter. So I have it set up as an ohm meter, and I will first connect the meter across the 6.8 kilo ohm resistor, measure the resistance. You'll see it is 3.12 kilo ohms. I will then connect it across the 3.9 kilo ohm resistor, making sure I have a good connection here. This is tough to do with only 2 hands. And notice the resistance changes to 2.708 kilo ohms. And finally, make sure I get the right one. I have the ohm meter across the 2 kilo ohm resistor. If I do this correctly. Okay, I am struggling here. There we go. And it is 1.68 kilo ohms. So once again, we see that depending upon which 2 terminals you measure, that's going to change which resistors are in series. In this case, these 2 resistors are in series, and then that combination is in parallel with this one. And you could actually work the math out yourself, with this being 2K, 6.8K, and 3.9K. 3.9 plus 6.8 in parallel with 2, you should get something close to this, with the understanding, of course, that these are the nominal values. The actual resistor values could vary by up to 5%. So anyway, this is just an example, a demonstration of the same concept that we just saw in the example. So we'll continue on with another example now.
For final example, let's look at another resistor combination and determine our equivalent once again by trying to find all of the resistors that are in series and all the resistors that are in parallel, combining them together, and then possibly, once you combine some, maybe revealing other series or parallel combinations. So if you look at the circuit here, you're asked to find are equivalent. And sure enough, if you were to connect this resistor combination up to an ohm meter, if you were to put an ohm meter here with a dial and actually measure the resistance, you would actually get a reading. There actually is an equivalent resistance here. The question is, can you find it using resistor combinations? So if you look at this, you're asked to see if there are any resistors in series or parallel. Well, unfortunately, you can look and look and look, and you're going to see that there are no resistors in series and no resistors in parallel. If you color code every node, see there's a node there, there's a node there, there's a node there, there's a node there, and running out of color, so we'll just put little red hashes in this one. So these are the unique nodes in this circuit. You will see that there are no two resistors that share the same two nodes. So no resistors are in parallel. Likewise, there are no two resistors that are the only two things connected to every node. Every node, the pink node, has 3 different resistors connected up to it. The blue node has 3 different resistors connected up to it. The green node, 3 different resistors connected up to it. You might say, well, wait a minute, how about this node on the bottom? Doesn't this just have 2 resistors, the 2 ohm and the 1 ohm resistor connected up to it? Yes, except there is this branch here that we're connecting to the multimeter, so the 2 ohm and 1 ohm resistor are not in series either. So the bottom line, there are no resistors in parallel, and there are no resistors in series. Because there are no resistors in parallel and no resistors in series, we cannot simplify this resistor combination using just parallel and series combinations. Once again, we are not saying that there is not an equivalent resistance. There certainly is. As I mentioned at the beginning of this problem, if you hook up an ohm meter to this resistor combination, you will get an equivalent resistance. We simply can't find it using the techniques that we know already. I do want to mention that there is a technique that would work in this problem called delta Y transformations. This is a topic we do not cover in this course. It is covered in the book, so I'll mention it. It is in section 3.7 in the book. The idea behind a delta Y transformation is if you have resistors, let's say in a Y configuration, you can convert them to resistors in a delta configuration where that node is the same as that node, that is the same as that, and that is the same as that. And there's an equation, a somewhat complicated equation relating these 3 resistor values to these 3 resistor values. How that could work in this problem is you could recognize that these 3 resistors here form a Y configuration. So using the delta Y transformation, we could replace them by these 3 delta connected resistors. Once you do that, we would see that this resistor here is in parallel with that resistor, and this resistor here is in parallel with that resistor. You could then combine these, you can combine those, and from there you'll see that there are additional series and parallel combinations which would allow you to find eventually our equivalent. I should point out that there might be some circuits where even the delta to Y transformations won't work. As I said before though, that doesn't mean that there isn't an equivalent resistance, it just means that you cannot calculate it mathematically. You could always measure it. So in our next class, we will learn 2 additional very useful theorems called the voltage division theorem and the current division theorem. These are 2 very useful shortcuts in simplifying circuits and simplifying your circuit analysis technique. We are also going to learn about a potentiometer, a very useful resistive device that we will use extensively in the EE210 lab. Anyway, for now, that is all. Have a good day.